Let's continue to talk about the hyperbolic functions. So we have our 6 hyperbolic functions defined as I have here on the screen. And now let's talk about if we have these functions, if we were to restrict them to be one-to-one, if they're not, which the only one that's actually not one-to-one that we need to look at is the hyperbolic cosine. But let's pause on that for just a second, knowing that we do have to have one-to-one functions, so if needed, we can restrict the domains. Let's actually look at the hyperbolic sine, which is a one-to-one function, and let's consider what would be the inverse of the hyperbolic sine. So if, and here we have our hyperbolic sine and our hyperbolic cosine, and those are exponential functions, and so if we had exponential functions, what would we suspect that the inverse of an exponential function might be? And if we think about that for a second, the inverse of y equals e to the x, of course, is y equals the natural log of x. So logarithms and exponentials have that inverse relationship. And so when I see a hyperbolic sine and a hyperbolic cosine in their exponential expansions, and I'm thinking, what would the inverses be? I am thinking their inverses are likely to have some sort of logarithmic definition. So how do we show that? Well, what we're going to do is actually start off with, let's consider the inverse hyperbolic sine, which would be defined, and we do know that it exists, by the way, because sine is one-to-one, exists since y equals the hyperbolic sine is one-to-one. If we kind of remember what that hyperbolic sine looks like, just graphically, it has that shape. So we do know that this inverse exists, but how would we actually come up with maybe an expansion in terms of something that we already know, like logarithms? How would we figure that out? So let's just consider this for a second. Kind of our thought bubble up here was, if these inverses could be defined, then it's likely to be logarithmic. Just knowing what we know about exponentials and logarithms and their inverse relationships. So let's take this and let's say if this is true, then if y equals the inverse hyperbolic sine of x, just using properties of inverses, by the properties of inverses, the hyperbolic sine of y, take the hyperbolic sine of both sides, has to equal x. But if that's true, the hyperbolic sine of y is just e to the y minus e to the negative y over 2. So 2x actually equals e to the y minus e to the negative y. Well, what am I going to do with this? If I want to solve for y, why don't we go ahead and get it equal to 0? So let's subtract the 2x, and I'm just going to flip-flop sides. I flip-flop sides up above. Maybe I shouldn't have. I should have just left it. So e to the y, and I'm going to put the minus 2x in the middle, minus e to the negative y equals 0. Just kind of reordering this, trying to solve this in terms of y, using what I know about exponentials and logarithms. So then I'm kind of looking at this, and it's kind of messy, and I don't really like the negative exponent. So I'm going to factor out an e to the negative y. So if I factor out an e to the negative y, that's going to leave me with an e to the 2y minus 2x e to the y minus 1. Now notice that this is actually quadratic. It's quadratic in nature. We could say let w equal e to the y, and we might be able to see that a little faster. So if that's true, this is actually w squared minus 2x times w minus 1. So notice that that is actually quadratic. And so if I want to solve this, since this is equal to 0, this is going to be equal to 0 if e to the negative y equals 0, or if our w squared minus 2x times w minus 1 equals 0, of course, where w is equal to e to the y. So we'll just leave that off to the side here. In a second, we'll have to substitute back in, but we'll leave it in its quadratic form for now. Now, first of all, this part, this is never going to happen because e to the negative y is always greater than 0 by properties of exponentials. Exponentials are always positive, always greater than 0. So there's no solutions coming out of that factor. So the only solutions for when this could be equal to 0 is when this factor equals 0, but it's quadratic. So let's use using the quadratic formula. We find that w, by the way, in the quadratic formula, my a is 1, my b is negative 2x, and my c is negative 1. So kind of keeping that in mind, and I'm going to come up here so I have a little more space. So w is going to be equal to 2x plus or minus the square root of 4x squared minus 4ac all over 2 times a. And so I get this expression 2x plus or minus, let's get this simplified, 4x squared plus 4 over 2, continue to simplify. There's clearly a common factor of 4, so we could pull that out, and then that works out nicely because that would simplify into 2x plus or minus 2 times the square root of x squared plus 1 over 2, which reduce that, and we get x plus or minus the square root of x squared plus 1. And that is what my w is equal to. Well, remember though that w was e to the y. So let's put our e to the y back in. So e to the y actually equals, remembering that w was e to the y, e to the y actually equals x plus or minus the square root of x squared plus 1. But we also know e to the y is always greater than 0 since it's exponential. And therefore, e to the y has to be only the positive root, because when you take the square root of x squared plus 1, that whole quantity, it will be larger in size than just x. So if we were to subtract, then this would actually be negative. So we're going to have to say that this e to the y is equal to x plus only the positive root of x squared plus 1. And we can continue down this road. Remember, we're trying to solve for y, so let's just take the natural log of both sides. And notice what we have just found is that y, which is, as originally defined, the inverse hyperbolic sine of y, is actually equal to the natural log of x plus the square root of x squared plus 1. And as we suspected from the very beginning, these exponential functions, if I can get it all, as I know it's kind of small, but if I can get it all on the screen there, these exponential functions, hyperbolic sine of x, does in fact have an inverse function that is logarithmic. So it is logarithmic. And all of them have logarithmic expansion. So let me go ahead, that's how we can prove this one has a logarithmic expansion, or show the logarithmic expansion for the inverse hyperbolic sine. But the others as well can be done in this way. So let's go ahead and project all of the inverse hyperbolics and their logarithmic expansion. So the inverse hyperbolics, just like the trig functions, we do have to restrict some of them in order to force them to be one-to-one, because inverse functions only exist for one-to-one functions. So you have to have a one-to-one function. And so for the hyperbolic cosine, for cosh of x, we actually have to restrict it to the domain to be from 0 to infinity to make it one-to-one, because it is not one-to-one. Remember that the hyperbolic function has that sort of shape, almost like a parabola. So we do restrict it and make, just look at the right arm of it essentially, so that we have a one-to-one function. Okay, once they're one-to-one, then we can have inverse definitions, and here are our inverse definitions. So the hyperbolic, inverse hyperbolic sine, as we've just proven, is the natural log of x plus the x squared plus the quantity x squared plus 1 under square root. And inverse hyperbolic cosine is the natural log of x plus the square root of x squared minus 1 as long as x is greater than or equal to 1. And inverse hyperbolic tangent is 1/2 natural log of 1 plus x over 1 minus x, as long as x is between -1 actually and 1. And here we go. Here they are all on. Here they are all in one spot with their restricted domains if necessary. The inverse hyperbolic sine, of course, does not have a restricted domain, but the other two do. And there you have it. Okay. And at the bottom of the screen here, we've already done that. We did do that proof at the beginning of this video. So you can follow along on your worksheet with that proof if you'd like to. I meant to mention that at the beginning. So if you were taking notes, it's actually on the worksheet as well. All right, so to wrap up our section on these new set of functions, so we now know what the hyperbolics are, we know what the derivatives of the hyperbolics are, we know how the hyperbolics are related to each other in the unit hyperbola. We also now have the inverse hyperbolics, and so the last thing we really need to talk about related back to calculus with these functions is once we have another set of functions, like the inverse hyperbolics, what would be their derivatives? So what would be the derivatives of these inverse hyperbolics that we've just defined, that we've just come up with? And we do know that these inverse hyperbolics can be written as logarithms, right? Connected back to their original functions, right? The inverse relationship with those hyperbolics, which are exponential in nature. So how could we find the derivatives of these hyperbolics? Well, we actually have two completely different ways that we could find them. And one of them is to simply use their logarithmic expansion. We know how to take derivatives of logarithms, so let's do it. So let's take the derivative. Let's do it for the hyperbolic sine. So let's take the derivative of the hyperbolic sine of x. And let's do it just by using what we know about logarithms. So what's the derivative of the log of x plus the square root of x squared plus 1? Quantity of x plus the square root of x squared plus 1. Well, using logarithmic derivatives, let's zoom in just a little bit, we know that the derivative of a logarithm is 1 over the quantity we're taking the logarithm of. So we'll just do that, and then we have to apply the chain rule. So this is going to be 1 over x plus the square root of x squared plus 1, but then we have to multiply by the derivative of the inside. Well, what's the derivative of the inside? Well, that's a sum. So it's going to be 1 derivative of x plus, and then we have to take the derivative of that root, which is also chain rule. So we'll have 1/2 times x squared plus 1 to the minus 1/2. I'm thinking of this as a 1/2 power rather than a root. Then we have to multiply by the derivative of the inside, which is 2x. Okay? And then we just have some simplification to do here, because of course that is the derivative, but we would want it to be in its most simplified form for our formula. So x plus the square root of x squared plus 1 times, then we get 1 plus x over the square root of x squared plus 1 when I simplify. Drop the negative exponent down and reduce the 2's and put the x on top. And so then we would want to probably, let's see here, let's go ahead and 1 plus x squared over square root of 1 plus x squared. Let's find a common denominator here. So this part becomes in the top x plus the square root of 1 plus x squared. And in the bottom, the square root of x squared plus 1. And notice over here we have 1 over x plus the square root of x squared plus 1. Which worked out well because notice that this and this are exactly the same. So those two cancel, and we end up with 1 over the square root of x squared plus 1. So it turns out that the derivative of the inverse hyperbolic sine is 1 over the square root of x squared plus 1. Again, connections back. Notice, it's not the same, but it's real similar to what the inverse trig functions look like. So remember, if you can remember back to what our derivatives of all of our inverse trig functions are, the derivatives of the inverse hyperbolics are similar in their structure with these roots and squares and so forth. Okay? And then we're going to get a whole new bank of derivatives. So that's one way to find the derivative of the inverse hyperbolic. But there is actually another way. It's the way we actually proved the derivatives of the inverse trig functions. So let's do one more quick proof, show that we get the same thing, and then we can compare. And now that we have all these tools in our toolbox, we just have so many more ways to do it. So if we say, consider y equals the inverse hyperbolic sine of y. And if we want dy dx, okay, what we could do is we can use implicit differentiation, because I do know the derivative of the hyperbolic sine of x. I do know that derivative. So if I could say, well, if this is true, if y equals the hyperbolic sine of x, what I could do is I could say, well, then that means that the hyperbolic sine of y equals x. And if I take the derivative implicitly on both sides, then the hyperbolic cosine of y, dy dx, using what I know about the derivative of the hyperbolic sine, which is hyperbolic cosine, has to just be equal to 1. But that means that dy dx equals 1 over the hyperbolic cosine of y. But now we do know the identity that says the hyperbolic cosine squared of anything, so I'm going to say y, since we have y here, minus the hyperbolic sine squared of y is equal to 1. That's that connection back to that unit hyperbola. So that means that the hyperbolic cosine squared of y equals 1 plus the hyperbolic sine squared of y. Take the square root, and the hyperbolic cosine of y equals plus or minus the square root of 1 plus the hyperbolic sine squared of y. But hyperbolic cosine, whoops, I lost my hyperbolic, I lost my h. Let's get my h in there. Looks like I said cosine. Hyperbolic cosine of y is always greater than 0. It's actually always greater than 1, but it is greater than 0. So we know that this has to be just the positive root. And so up here we can put in that positive root, 1 over the square root. I lost the root too. Lost my hyperbolic and the root. So that should have been a hyperbolic, and that should be the square root. I got going on the plus and the minus. 1 plus the hyperbolic sine squared of y. But the hyperbolic sine squared of y is equal to x. That's what we did. We had to use that inverse property and write the hyperbolic sine of y equals x in order to take this derivative implicitly. So what that all means is that this is actually just 1 over the square root of 1 plus x squared, or rewrite it as we did on the other side, and we can say, therefore, the derivative dy dx is equal to 1 over the square root of x squared plus 1. Or 1 plus x squared, however we want to write it. Obviously, those are the same thing mathematically. And there is your derivative of the inverse hyperbolic sine proven in 2 different ways, using implicit differentiation or just using its logarithmic expansion and what we know about derivatives of logs. So we actually can find those derivatives of those inverse hyperbolics in 2 different ways. You sort of choose your way you want to prove those, but we get this derivative, 1 over the square root of x squared plus 1. So that said, that gives us a whole new bank of derivatives that we can add into our useful derivatives. And let me project that on the screen to end this video. And here we have a whole new set of derivatives, the derivatives of the inverse hyperbolic functions. And so again, remember that these can be proven or shown. These formulas can be proven or shown using either implicit differentiation or just using the log expansions, which is what we did for this guy, for this inverse hyperbolic sign. And the others can be proven in a very similar way. And there we have the derivatives. And again, notice there's quite a bit of similarities to the derivatives of the inverse trig functions. And so, as I mentioned at the beginning of this section on the hyperbolics, these hyperbolic functions are a whole new type of function for us, but they have so many connections to functions that we already know. And they are, as I mentioned, I say this in all the calculus courses as I teach them, up through Calc 3. If you remember these inverse hyperbolics and the hyperbolics and all of the connections, they can become very useful and handy. And so rather than working with complicated exponential functions, you can work with these hyperbolics and the relationships of the hyperbolics.